All right, so this is paper 2 of May 2016, time zone 0. All right. Question number 5, part B. We're told that a probe is launched vertically upwards from the surface of a planet with a speed v equal to 3 over 4, um, 3 over 4 of the escape velocity. Well, this should be v. All right. The planet has no atmosphere. Determine in terms of the radius of the planet R, right? The planet capital R, so we have to determine, okay, the maximum height from the surface of the planet reached by the probe. So I draw this quick sketch. So this is the radius capital R of the planet. Here is the surface of the planet. And now this is the height traveled by the probe with an escape velocity 3 over 4. With a velocity of 3 over 4 of the escape velocity. And so we have to find h in terms of r. Okay? Now, here's some of the formulas that came in my mind when I was solving it myself. So we know the escape velocity is radical 2 gm over r. Then we have work equal to mass times the change in gravitational potential. And we also know that work is equal to the change in kinetic energy. So if you put these two equal to each other, we'll have kinetic energy final minus kinetic energy minus the initial kinetic energy, which is 0. So 1 over 2 mvf squared is equal to m, the change in gravitational potential, which is um, the final gravitational potential is negative gm over h plus r, right? This is h, and then plus the radius of the planet plus r, and then minus, which will be plus gm over r. This is the initial gravitational potential at the surface of the planet. So obviously let me see if I can, the masses cancel out. And now you can substitute in v, it's going to be 1 over 2. I'm going to square it right there. 9 over 16 v escape velocity squared equal to negative gm h plus r plus gm over r. Okay, so now we want to find h, right, in terms of r. So we have to find a way to get rid of this escape velocity. So you can substitute in this for here. So you can rewrite this as these escape velocity squared is equal to 2 gm over r, and you can substitute that in here, and you'll get 1 over 2, 9 over 16, and this is 16 by the way, not 10, times 2 gm over r equal to negative gm over h plus r plus gm over r. So your 2's cancel out, 1/2 and 2 cancel out, obviously. And what else? Gm over r. Wait, let me simplify this before canceling out anything. So this is going to be 9 over 16. 9 gm over 16 r, right? Plus, I'm going to bring this term to the left, plus gm over h plus r equal to gm over r. So now you can cancel out gm, right? And we can write this as 9 over 16r plus, maybe I think it was a better better idea to bring GM over R to the left instead of H plus R. So I'm going to do that right now. So this is going to be minus, and I'm going to find the common denominator. This is going to be 16 GM over 16R equal to, I'm going to put this back where it was, so minus GM H plus R. I'm sorry, GM is cancelled. So 1 over H plus R. All right. So 9 minus 16 is negative 7. Negative 7 GM over 16R equal to negative 1 over H plus R. So your negatives cancel out. Now, if you do some basic algebra, why did I write GM? 7 over 16R. Okay, so now if we do basic algebra, we'll take 16 there, H plus R here. So 16 divided by 7, 16R divided by 7. Then minus R is going to be, so I solved it for the sake of saving time. It's going to be, H is going to be 9R over 7. And that's how you solve for H in terms of R. Or for part C, we're asked that we're told that the total energy of a probe in orbit around a planet of mass m is e to the power of negative g mm over 2r, right? And we're told that a probe in low orbit experiences a small frictional force. So just the effect of this force on the speed of the probe. Well, for this question, you have to visualize it, I guess. So frictional force will, of course, when the probe is acted by a frictional force, the total energy of the probe itself decreases. But for this question, you have to imagine the probe and the orbit around the planet somehow similar to that of an electron orbiting a nucleus, right? Like if you imagine it that way, if your total energy, if your energy of the electron decreases, right, it will come closer to the nucleus. And so for this case, or in this case as well, when the total energy of the probe decreases, the radius of orbit decreases as well, and therefore the orbital speed decreases because the orbital speed increases, my bad, since the orbit is radical gm over r, right? So this r is the radius of the orbit. And so that is how, ladies and gentlemen, you answer this question. Hope that helped.